Okay, now it's the turn of Masedi Masekane from RADIATE, and we are very happy to hear about RADIATE opportunities.
Thank you very much. So following Nicolas's talk, you heard that electron microscopies can give you, well, you may know that can give you structural information about your materials at very high spatial resolutions. So what we wanted to do here was to demonstrate that ion beams could be suitable as complementary methods to your analyses. And so to do that, I'll start off by just briefly telling you what RADIATE is about. So RADIATE was established in 2019. And this is basically a network of ion beam facilities, or facilities that use accelerated charged particles to either modify materials or to analyze materials. That's as succinctly as I go as far as it. And we use ion beams ranging from protons all the way to heavy ions. And we we can probe materials at varying depths. So this is quite applicable to a number of materials, ranging from energy all the way to cultural heritage. To really demonstrate the expertise of ion beams in RIANA, we've structured the presentation to show you 3 tiers of ion beams, of ion beam provision. First one being ion beam analysis. So as the name suggests, in principle, we use accelerated charged particles to analyze materials. So when the ion beam interacts with your material, you have quite a number of reaction products, photon emission and scattering reaction products. And you use these to probe and quantify the composition of your material. So in essence, if electron microscopies tell you the structure of your materials, ion beams can tell you what your materials are made of. So we can give you compositions in the lateral plate. We can also tell you the distribution of materials in terms of depth. And this is really sensitive to both light and heavy elements, so ranging from protons or hydrogen all the way to uranium. We are also able to separate or quantify elements in terms of their isotopes. And we recently have a new junior scientist who will be joining soon for accelerator mass spectrometry. And what we are able to do with this is we are able to do ultra trace isotope detection, so in the PPT range. So the use of ion beams is really quite versatile in the sense that you can tune or choose what type of ion beams to use, really to gather as much information as you can from this. So our sensitivities are typically in the nanometer to micrometer range for depth profiles, really depending on what technique you are looking for. Well, the interesting point about the beam being non-destructive, this really depends on the type of material you're using. But destruction could be thought of in different forms, which brings us to the second part, ion beam modifications. So you can use the ion beam not only to analyze the material, but to modify it in the sense that, well, you can implant certain energies and materials for defect engineering, or you could simulate harsh environments, like in a nuclear reactor, for example. And you can then complement this with other techniques, including ion beam analysis as well, to gather more information about how your material behaves in certain environments. Now, aside from high energy ions that we typically use in the MeV range, you could also go to much lower energies, to a few tens of keV ions. Now, this is quite interesting. At these low energies, you are able to focus the ion beam a bit more, which means that you have a really good spatial resolution in the nanometer range. And how this complements techniques like TEM, for example, or SEM, is that you are able to really control how far you go in the sample, especially if this is if you're looking to do a surface analysis, for instance, then FIB or helium ion microscopy, for instance, is quite a good technique to use. So really, ion beams is quite good complementary methods. And another advantage is that you can use FIB for insulating materials. And we've just given you quite a number of examples for what you could do with FIB. You could do milling. You can introduce quantum defects. And you can also do similar to ion modifications. You can do this at really low energies and really localized regions. In essence, we can compartmentalize what ion beams can do for you in really 4 sections. So you can get both qualitative and quantitative elemental distributions or compositions of material. You could determine your depth distribution of these elemental species or atomic species and materials. And you can simulate different environments or testing your material for how it behaves in different environments. And because these capabilities span from both from nanometer to micrometer range, it's quite versatile and quite applicable with other methods as well. So well, that's actually 16. We have 16 partners in the RADIATE network, and this covers from high energies all the way to low energies. And these are the, oh, we don't have the other picture. Sorry, Miriam. These are the junior scientists who are working on the RADIATE network as part of RIANA. And we actually have a beautiful poster on ion beam modifications by Santanu, which you definitely have a look at that. And I'm opening the floor.